Good evening, everyone. Can you hear me? Good evening, everyone. Can you hear me? Good evening, everyone. Can you hear me? Okay, great. So let's see. So before we start the review, I want to go over the topics that will be covered in your exam. So let's see. So before we start the review, I want to go over the topics that will be covered in your exam. So let's see. So before we start the review, I want to go over the topics will be using the basics of Boolean algebra, logic gates, SOP, PLS, and the simplification of Boolean functions. For the combinational logic, and for combinational logic, the topics will be decoders, encoders, multiplexers, demultiplexers, PLDs. That includes PLA, PAL, ROM, tri-state buffer, half adder, full adder. Yeah, I heard the echo too, so let me tri-state buffer, half adder, full adder. Yeah, I heard the echo too, so let me tri-state buffer, half adder. How do I fix this? Okay, let me see if this fixes the echo problem. Sorry about that. Can you still hear the echo? Okay, great. So yeah, let's go over the basics again. So for this exam, you are expected to know the Boolean algebra logic gates, sum of product, POS, which is the product of a sum, simplification of Boolean functions already before. So you will be able to apply it to combinational logic and sequential logic. For combinational logic, you will be having to design decoders, encoders, multiplexers, demultiplexers, PLDs, which stands for Programmable Logic Device, PLA, PAL, ROM, as well as tri-state buffer, half adder, and full adder. And for sequential logic, we will be going over latches first, and the structure for it are NOR SR, NAND SR gated, and D latch. The next one will be flip-flops, which includes D flip-flop, JK flip-flop, T flip-flop. The register will be comprised of flip-flops, which is the application part of sequential logic, as well as shift register, bus holder, and switch debouncers. Now, so for switch debouncer, I have no knowledge about what your professor did for that, so if any one of you can tell me about that, that would be great. So let's go over the first topic, which is the decoder. We know the definition of decoder is defined as follows. let's do a 2 by 4 decoder first. The way we are going to draw this component is as follows. Because we are going to have 2 inputs, will be our LSB, MSB, and the reason we label LSB and MSB is because we want to know the addresses. For example, if we have 0, 0, this is address 0, 1, 2, 3. We know the first output will be, let me switch the input first. So let's do the MSB for A and LSB for B. We will get the output at address 0 to be A0 ANDed with B0. The second one will be A0 B. The third one will be A B0. The final one will be AB. And based on this function, we will be able to have the structure of the decoder in gate level design to be followed. And so on. We apply the same concept for the larger decoder, which is 3 by 8 or maybe even 4 by 16. And that covers the decoder part. Is there any question so far? Okay, let's go over encoder next. The encoder is basically the reverse of decoder. And take the previous example, we will have our address 0, 1, 2, 3 here. And we will have our output here. So basically, if we have a 1 here, we will have an output of 0, 0. Assuming the rest will be 0. If we have 1 at address 1, we will have 0, 1. And we apply the same concept for the other inputs. So the combinational logic part will be quite simple, so I will not spend too much time covering those. And the next one will be multiplexer. How do we define the multiplexer? Basically, we will have multiple input. Take a two 2-to-1 multiplexer as an example. We again will have address 0 and address 1. Because this is a 2-to-1, so we know the selector will only be 1 bit. So, we know when selector is input a 0, it will select this line, pass through the output. If the selector is 1, then it will select this line and pass through the output as well. Therefore, if we name the variable of the mux, let's call this A and call this B, we know the output can be written as A S0 naught or B S0. Okay, so how do we express this Boolean function in gate level schematic? We will have input A and input B, as well as S0. We know A ended with S naught, so this term will be inverted. The output right here gives us A S0 naught. The second one will be B S0. For the output, we know two terms are ORed together. So this is our mux circuit in gate level design. And one application for the mux is your TV at home. For example, if you have cable and HDMI, or the other one may be antenna, you may have, let's just assume we have two input. Let's say this is cable and this is your HDMI. And when you use your remote to select which input to pass to your screen, you will have to select 0 for cable and to select 1 for HDMI. And this covers the multiplexer. So let's say we have a function of f, x, y, z. It's supposed to be an OR here. The way we can express this using mux, let's say we have a 4-to-1 mux. We know we will have a selector of 2 bits. say this is F. If we pick our X, Y to be our selectors, we can see that there are no repeating terms here. This is 0, 1. The next one will be 1, 0. And XY will be 1, 1. So let's connect X to S1 and Y to S. We will see at 0, 1, this is address 1. We know X0 and Y is ended with Z. So we will connect Z to address 1. The next one is 2, address 2. It is also connected to Z. So we connect this together. The next one is address 3, which is this one right here. However, for this one, this requires a inverter, right? And your homework problem, I believe, your professor asked you to only express this Boolean equation using only mux without any other logic components. And in this case, we have to check if there's other way. If there's no other way, like for this Boolean equation here, we have to use a 8 to 1 mux. Therefore, we will have 3 bits selectors. Let's call it S0 and to S2. So we will have, let's connect X, Y, Z to each. Going back to the Boolean equation we have above, we will see this is 0, 1, 1, which is address 3. We will connect a 1 here. The next term is at address 101, which is 5. And then we connect 1 at address 5. The next one will be 110, which is address 6. For the rest, we will connect 0. Now moving on to Shannon expansion. If we have f x, y, z equal to x or y or z, and given let's say 4-to-1 mux. How do we express this equation using the 4-to-1 mux? So to do this, we have to select either xy, yz, or xz as our selector. And let's assume we are selecting xy in this case. And notice that each term does not all contain the y or the x. So we have to do the Shannon expansion for each term. Let's take x as an example. We know in this term y is missing. So to do the Shannon expansion, we know x ended with y or y naught. This is 1. So we know the equation is equal to each other. This will become xy or xy naught. Now we're finished with this term. We will do y. We know that x is missing, so y has to be ended with x or x naught. To expand this term, we will have x, y, or x naught y. The last term will be z. Now z is missing to both x and y. And to do this step by step, we can do x first. This will become zx or zx naught. And we can do the Shannon expansion for this, that we have to contain the y in the term. So zx also equal to y or y naught. How about zx naught? Applying the same logic. This will become zx naught y naught. Now we got a function of expanded x, which is x, y, or x, y naught. Why expand the term? Now, C expanded is let me write down here. This will be C x naught y or C x naught y naught. So this is our we now have two selectors because this is a 4 to 1. And for our previous selection, we selected x, y to be our selector. So let's put x, y here. Now looking at the Shannon expanded function here, we have x, y repeated. We can combine them. xy is going to give us address at 1, 1, which is going to be address 3. So we put a 1 here. So how about x, y not? We notice that in our term, we have a repeated selector, which is ended with z. So we factor out x, y not. We will get 1 ORed with z. This term will be 1. This address will give us 1, 0, which is address 2. So we put a 1 here. The next one is also repeated with z. So x not y, 1 or z. This will just be x not y with 1. This address is going to be 0, 1. So address 1, so this is 1. And I miss a term for address 1, 1. This here is 1 as well because x, y can be factored out and 1 ORed with z, it's still 1. So at address 3, this is still 1. And we took care of all the previous term already. Let's do, this term is cancelled already. And the only term we have left is z, x naught, y naught. X naught, y naught gives us 0, 0. The address is 0. So we can put the z here. And to answer your question, Esther, how do you know what size specifically to use and try out? It depends on the problem given by your professor, right? If you're only allowed to use multiplexer without any other logical elements, you will have to factor this. Like for example, we are required to use an inverter here because of this term, xy ended with z naught. Previously, we selected X to be our S1, Y to be our S0. So this is going to give us address 11, which is address 3. In order to get Z0, we have to put it into an inverter. And this is simply not going to work because the problem asks you to design the circuit only using mux. And that's why we use 8 to 1 multiplexer instead, because we will be able to put our inverted Z to our selector. Does that make sense? Yeah, so if we branch from the other Z input and invert it for input 3, we're still using the restricted gate, right? This is an inverter. But if the problem asks you to use only mux, then you will not be able to have inverter in your circuit. If we going back to our gate level schematic for our mux, we can see the only place that has the inverted value is this one. It's our selector. Does that make sense? Okay. We can go to the next topic and have more problems to do back at the multiplexer. So the next topic will be the multiplexer. The purpose of this is the opposite of mux. And let's have a 1 to 2 demux as an example. We will have only one input. And in this case, because it's 1 to 2, we will have two output. We will have only one bit select line in order to select which output to pass the input through. For example, if I have a 0 inputted into the selector, at address 0, we will be able to pass the input here. If I have 1 here, this will be passed the value of the input. Therefore, we can write an Boolean function as in S0 not. This is in S0 and So basically we have two output. Our input is here. Let's say this is the output at address 0. This is output at address 1. Input connected here. This value here is inverted. This is connected to the select line as well. So we can see this is in, ended with SO. This is in, ended with SO not. And application for this problem is that you will have, for your TV as your example, you will have a screen, and most of the screen is only takes the serial input. So basically you can have a pixel here and a pixel here, and this one will be connected to a counter of some sort, but this is 1 bit, so we can just say this clock. So when the serial input comes in, based on the serial input here, we will be able to determine the pixel to turn on and turn off. And usually the clock frequency is really high, so you will not be able to see the pixel turning on and off. You will be able to see that the pixels are always on and changing the value. Let's go back to the topics, and that covered the multiplexers. Is there any questions so far? Okay, let's go over PLD. For PLD, we have PLA. PLA stands for Programmable Logic. That means it's programmable and structure, as well as programmable or structure. And the way we're going to draw this, let's say we have a Boolean equation here first. Say we have A, B, C, or A, B not C, or A not B not C not. We will have an input here. This is our A. For each input, we have to have an inverted value. So how do we express this with logic gates in PLN form? We will have an AND gate, a horizontal line across the input. The first term, this is going to express our first term. This is going to express our second term, third term, and maximal fourth term. And to make connection, to show the connection, we can put an X. The first term is ABC, so we put X over here. The second term will be A, B naught C. So we put an X at B naught location, as well as C. The third term will be A naught B naught C. The fourth term will be A naught B C naught. And since the PLA is programmable, we know we can simplify our AND structure. We can simplify this using either K-map, but in this case, because our Boolean equation is really simple, we can just do AC, factor this out. This will be 1. And for this term, two term, we can factor out A naught C. No. Therefore, our simplified equation is AC or A naught C naught. Therefore, we now have only two terms. Erase the connection here. The B connection to B is gone, so we can only use two input AND gate. The second term will be A naught C naught. To finish this PLA design, we will have an OR gate to express our SOP output, which is equal to AC or A naught C naught. For this example, we only have one output, but actually in reality for PLA, we can have multiple outputs. We may have, let me make a connection. We may have another OR gate for another output. Let's call this F1. We may have F2 as well. Assume our F2 is A naught B naught. or A naught C naught. Because our OR structure is programmable as well. We can actually share the AND gate, AC repeated, and only draw one AND gate for A naught B naught. Make the connection, and this one will use the repeated AND gate for A naught C naught. And the idea for PLA is very simple, so we can move on to the next topic if there's no question. The next one will be PAL. This stands for Programmable Array Logic. This is only programmable for the AND structure. It has the fixed OR structure. What this means is that in PLA we have our AND structure to be simpler. We're able to simplify our AND structure. In PAL, we will still be able to simplify our AND structure. However, for OR, it has fixed connection. Therefore, we cannot select which connection, which AND gate to connect here. Let's use a previous example. So we have F1 to be AC or A naught C naught. F2 is okay. So since the AND structure is still programmable, we can have connection here, A and C for our first term. Second one will be A naught C naught. And then the third one, which is A naught B naught. Now for PAL, you may only have a 2-input OR gate. Maybe you can have you're given a 3-input OR gate as well. So if we only have 2 input, we can only have 2 terms here. The OR gate will have fixed connection. Let's assume the fixed connection is connected to the first and second AND gate for this one. However, if we are only given an OR gate that has connection at this and this location, the output here will be AC or A not B. Therefore, we cannot realize this function here. But I believe on your exam, if your professor has this problem, he will tell you the limitation for the OR gate. But the idea here is that the connection here is fixed and the number of input is fixed. So if you're only given 2 input, then we can only use 2 input OR gate without using any other 3 or 4. Now the next topic will be read-only memory. So read-only memory means that we will have fixed and structure, but programmable. Or structure. And usually for the AND structure, we use decoder for that. Let's go back to our PLA example. We have our F1 to be simplified. We simplify into AC or A naught C naught. For F2, we have AC, A naught B naught or A naught C naught. Given these two equations, we know it has to be at least a three input decoder, because we have AC here. However, we have A, B, C here. So let's draw the decoder. set our A to be our MSB. Because it's a 3 input, we know the address will go from 0 to 7. And knowing the definition for decoder, we can have an output here of A naught, B naught, C naught. For 3, we have A naught, B, C. 4, we have A, B naught, C naught. 5, we have A, B naught, C. For 6, we have A, B, C naught. For 7, we have A, B, C. And now going back to this term, we see that this term doesn't contain AB. So we will have to do a Shannon expansion for that. For this term as well, we have to do Shannon expansion to get B into each term. But previously, if we use the unsimplified version of F1 here, we can already have all the variables in each term. So F1 equal to ABC or AB not C, A not B not C not. And this is just to show you that if we are given a if the problem asks you to design a ROM-based logic circuit, you cannot simplify the end structure of your Boolean equation. Therefore, we will have an output here of F1. That's going to be connected to some of the terms some of the addresses from the decoder. So for F1, we need ABC, which is address 7, AB not C, which is address 5, A not B not C not is address 0. Back to our POA example, we have F2 to be equal to A not B not, or A not C not, I believe. Yes. And because this is already given in the most simplified version, we have to do a Shannon expansion for this, which is A not B not ended with C or C not. This term here will be A not C not ended with B or B not. Therefore, we will have A not B not C or A not B not C not, A not C not B, No. Okay, let's reverse the order here a bit so we can have ABC. And notice that these terms are the same, so we can eliminate this one. Let's see. This one here is address 0. This one here is address 1. This one here is address 2, I believe. Sorry, I erased the. This one's supposed to be A not B, C not. Therefore, we will have a connection as follows. A not B not C, which is this one here. At address 0, we have a connection here. And address 2. So this is how we convert our Boolean equation into ROM logic. And we call this a 8x2 ROM. The number here is the number of addresses. And the number here is the number of outputs. Okay, that covers all the PULDs. Is there any question before we move on to tri-state? Okay, so tri-state buffer. This is the logic symbol for tri-state. This is our input here. This is our input. We will have one output. And there's another variation for tri-state, which is the inverted value. To draw the truth table for this one, let's say this is input A, and let's say this is input B. Now, when B is 0, that means it's going to turn off this tri-state buffer. And by turning off, it means that it's going to give the high impedance when looking from the output. So basically, we can, from this truth table, we can simplify the circuit. So the switch will close when B equals to 1. We can see that when B is 1 and then switch closes, we will have the value of A passed to the output. So this will be 0. This will be 1. So tri-state, 3 state, 0, 1, and high impedance. For other variation of the tri-state buffer, we again have AB to be our input. However, this time, because our bubble here, that means that B is inverted. So whenever B is 0, that means it's going to pass the value of A to the output. When B is 1, that means the switch is open. That means we have high impedance. Therefore, that concludes the tri-state truth table. One application for tri-state is what I'm about to draw. Say this input 0, say this input 1. We connect the outputs of the tri-state together, and this will give us an output. Let's say this is the inverted variation of the tri-state. Let's say this is non-inverted. If we put S here, we know that when S is equal to 0, the tri-state buffer here will pass the input value to the output. However, when S is 0, this is like an open switch. So this is high impedance when S is 0. When S is 1, this tri-state is off, so high impedance there. And this tri-state will be on. That means the input will pass to the output. Therefore, we can derive a Boolean equation to be in 0 ended with S0, or in 1 ended with S. We can see that this equation is the same as the equation for mux. This is a 2-to-1 mux. So it's not really an op-amp. It's a this is like an inverter. So the buffer is like an inverter connected to another inverter. But if you're going to take VLSI in the future, there's actually going to be, this is like an enable here. Hello? I'm doing the test review right now. So are you in the review session? Okay, so I can help later once I finish the test review. Bye. Yeah, so to answer your question, this is not related to your exam. This is going to be really advanced video SI. We know the inverter's transistor level is VDD. And just a brief explanation. And this will be like the NMOS, and this is the PMOS. Input are connected together, and therefore if we input the 0, if we ground this, VDD will pass to the output. If this is 1, then ground will pass to the output, which means that this is the inverter, right? And tri-state buffer is actually related to tri-state inverter, where we have an enable. This will be enable not. This is our input. So this is actually enable not enable, kind of like this. Sorry, so off topic here. So let's go back to the tri-state. So as you can see in the previous example, the application for tri-state is to make a 2-to-1 mux. And we know that from 2-to-1 mux, we can build a higher level muxes like 4-to-1, even 8-to-1 till 16-to-1. Therefore, using the tri-state buffer, we will be able to build all the available input muxes. Does that make sense? So that covers our tri-state buffer. Then we can move on to our half adder. Now, the truth table for half adder is as follows. We're basically doing addition in binary. Let's say we have A and B. We want to add A and B together. We will have a sum. We will have carry out. Notice that 2 of these are outputs. These 2, however, are inputs. if we do addition in binary, this is like this. 0 added with 0, this will give us 0. Carry out is 0. However, if A is 0, B is 0, this is also going to give, no, not also, this will give us 1. The sum is 1. And we can see A plus B, 1 plus 0 is still 1. The sum for 1 plus 1 is actually going to be 0, and then carry out will become 1. Let's erase our 0. Which means we will have two output. Let's take a look at sum first. We can see AB at the location of 1, at 1 here. This is going to be equal to A not B or A B not, right? This is actually going to be an XOR. I believe it's a circle plus, yeah. So we can use an XOR gate. This is sum. Now we took care of the output sum. We want to take care of Cout now. Cout is equal to A ended with B. Therefore, we can see A and B are connected to an AND gate. This will be your half adder circuit here. How about for full adder? We will have A, B, and the capability of having a carry in as input. We will still have sum. And the second one will be Cout. Truth table. Now the addition is like you're adding A, B together, but you might have like Cin right here as well. This will give us sum. Now the carry out will be in this location here. So 0 plus 0 plus 0, it's 0. If our Cin is 1 and AB are 0, we will actually have a sum of 1. And same thing for B is 1. However, in the next one, we have B as 1, Cin as 1, and A as 0. So if we come back here, this is 1 plus 1. Because of carry in, we will have a Cout of 1. And sum is 0. And by following the same logic, we will have 1 here. We have 0 here. Carry out is 1. And then this one will be 1 and 1. Okay. Now let's take a look at our output sum. This is 1. Therefore, we know sum equals to now we know these 4 will be an XOR. Actually 3. These 3 will be XOR because A not B not C or A not B C. This term here will be XOR. Which is A XOR B XOR C. Now we haven't taken care of this term, which is going to be ABC. Simplifying the equation above, we will have A XOR B XOR C ORed with ABC, I believe. ABC OR gate. Is it? I believe so. So this is our sum. Now back to Cout. This is A not B C in. This is A B not C. B C and not. See. Okay, can we simplify this? Let's see. So I see that we can simplify these two terms, which is just A, B, and C in or with C in not will be 1. And I think that's it. So our carry out will be we simplified this already, so it's just AB. Therefore, we will have 3 input AND gate with inverted A, B, C. And 3 input OR gate. Another 3 input AND gate with inverted B, Cn. Now we have AB. This is our C out. Interesting. I feel that I did something wrong here. Let me make sure, double check. For some, we will only have, it seems that we only have a 3 input XOR for the output. Interesting. But according to the truth table, this circuit here should function without any problem. Anyone knows what went wrong? It's okay, but this circuit here should not give you any problem because we did it based on the truth table. Because A plus B plus C n will give us a sum of 1, right? And then CL will be 1. And we know this term right here will give us XOR of 3 input. just that somehow for the full adder, it's actually only, the sum is only XOR. Let's see. Okay, we can come back to this later. Let's go to flip-flops and latches. So the first one you will encounter are latches, and the definition for latches are that it is level sensitive. By level sensitive, it means that it's going to check the level. So below we have SR latch or NOR based. And to trace this, we can look at the table here, that whenever there's a 1, whenever 1 is inputted into the NOR gate, it's going to force the output of the NOR gate to be 0. However, if whenever there's a 0, it's actually going to be, the output is going to be dependent on the other input because of 0 here. And we know for this row, there are only 1s. So if 0 is inputted, we know that it can be either 0 or 1 for the output. Therefore, we have a truth table here. And we're defining set, when set equals to 1, then our Q will become 1. When reset is 1, then Q naught will become 1. So let's see. Let's say we have 1 as S first and 0 actually S at 0 first, and then R to be 1. Now going back to the statement below, we have whenever 1 is input into the NOR gate, it forces a 0, right? So reset as 1 is going to force the NOR gate to have an output of 0. Therefore, 0 is going to pass to the upper NOR gate. We will have a 0, 0 function here. So we have 1 here. And because we want S, whenever S equal to 1, we want Q to be 1. Whenever R is 1, we want it to reset, so Q naught will be 1. So this will be Q naught, and this will be Q. Now let's go to when S is 1 and R is 0. So this is 1, R is 0. Now we have this NOR with a forced output of 0 because S is equal to 1. And 0 is going to pass to the below NOR gate. So 0, 0 is going to give us 1 here. So we know this is, we have Q to be 1, Q not to be 0. Now if we look at the next statement, we have 1 and 1. And based on the truth table of NOR 2, we know both output will be 0. But this one will be our undefined, because we always want Q to be the opposite of Q naught. So X here. And let's say we have SR to be 0. This is 0. Now, looking at the truth table for NOR 2, we know that whenever the 0 is inputted into the NOR gate, it's actually going to be dependent on the other input, because when 0 is inputted, then it can be, the output can be either 0 or 1. Now, let's assume we have a value of 1 here for Q naught and the value of Q to be 0 here. For the below or NOR gate, we have 1, 0 or 0, 1. We see these two rows is going to give us 0 as our output. So it stays the same. And the 0 here is going to pass through the upper NOR gate. 0, 0 is going to give us an output of 1. So this one here stays at 1. So we can say this is a storage. Or we can say no changed. So this will be a NOR-based latch, SR latch. We basically follow the same logic for a NAND. However, the only difference here is that whenever there's a 0, output is forced to be 1. Then we can trace the table again. Q, Q naught. Let's start with 0, 0 first. If we have 0 for S and 0 for R, we know 0 for R is going to force the NAND gate to have a 1 for output. Same thing for the upper NAND gate. This will have an output of 1. This is undefined. However, the next state will be when S is 0 and R is 1. We know the 0 is going to force the NAND gate, upper NAND gate, to be a 1. And a 1 is going to pass to one of the input of the lower NAND gate. So 1, 1 is going to give us 0. Like previous mentioned, we want to define that when S is 1, then it's going to set Q to 1. And when R is 1, it's going to set Q naught to 1. In this case, we have S to be 0, R is 1, so this is reset. So we want Q naught to be here and Q to be here. And following the same logic for the next one, which is S to be 1 and R is 0. So when 0 is inputted, it forces the value of output to become 1. So we look at the lower NAND gate first. This is going to become 1 for Q. 1, 1 is going to give us 0 for Q naught. And when S and R are both 1, it's going to be dependent on the other input, so we have to go back to Q naught and Q and see the feedback. So in this case, Q naught, let's assume that the previous case is that Q naught equals to 0 and Q equals to 1. Then 0, 1 input into the NAND gate is going to give us 1. And 1 go back to the upper NAND gate, 1, 1 again. We will have 0 here, so this is storage. The next one we will be talking about is a gated latch, which is, it enables a clock signal. And remember previously that the latch means that it is level sensitive. So it's either sensitive at 0, that means the value changes at 0, and if it is sensitive at logic high, then the value changes when the level is high. Now to fill this truth table, the gated latch, this is JK latch. So we will have Q and Q naught as follow. And to save time, I'm not going to trace through all of the path, but the definition for JK we will see later is that 0, 0 is storage. 0, 1 for JK is going to be reset. By reset, it means that Q naught goes to 1 and then Q goes to 0. For JK equals to 1, 0 is going to be setting Q to 1 and Q naught to 0. When JK equals to 1, 1 is going to be toggle. However, for JK latch, emphasis on latch, this is actually a really poor function because it's really hard to control how long the duration of this is. And as long as as long as it is high, the output of Q will keep toggling due to the propagation delay. So this function here is not effective for latches. Therefore, we have a new master-slave flip-flop. And to make this, we basically connect two JK flip-flops together with an inverted clock to one of the clock. And flip-flop means that it is edge sensitive. That means it is sensitive at either falling or rising edge, depends on where you connect the inverter. In this case here, we know that when we have a clock of 1, it's going to, let me go back to the truth table for NAND gate. So when we have an input of 0, it's going to be forcing the output to 1, right? But when there's a 1, it's going to be dependent on the other input. So when clock is 1, it's actually going to activate these two NAND gate to allow the value of JK to be recognized and pass through the SR latch here. And if clock is equal to 1 here, this is going to be inverted, so clock here is equal to 0. And we know 0 is going to force the output of the NAND gate to be 1, 1. And we know if 1 is inputted into the NAND gate, it's going to be dependent on the other. So when looking at the output of Q and Q not here, this will actually be storage. We can go back to the latches. So 1 and 1 is going to be storage. Okay. But as soon as the clock goes to 0, this will go to 1. Therefore, enable this flip-flop to store the value here. So this is actually a falling edge sensitive. Which is shown in the waveform here. So at this point, we have to check the value of JK. And if J and K are both 0, this is storage. Whenever it's 0, 1, this will reset. 1, 0, this will be set. So this is Q to be 0 and Q to be 1. And this is the previous Q. And the real function for this is that it's going to give an advantage when we have a 1, 1 input into JK. This is toggle. We know the time for the clock to go from high to low is going to be really, really short. High to low. Therefore, it's going to be an easy toggle. Like previously for the level sensitive, the duration here is hard to control, so we might have multiple toggles. And for edge trigger, we will only have one toggle per clock cycle. Any questions so far? So we have covered JK flip-flop. And the professor is also going to ask you to make T flip-flop and D flip-flop based on the JK flip-flop we created. Let's simplify the circuit above to this symbol, JK, Q, Q naught. So D flip-flop means delay. It means that whenever the clock goes from high to low, in this case it's high to low, Q will become D. So that means that when D is equal to 1 and then the clock triggered the flip-flop, Q will become 1. However, when D is equal to 0 and then the clock trigger, Q will become 0. And if we look at the truth table for JK, to make Q to become the 0, we actually want D to be 0 here and D to be 1 here. So to turn JK flip-flop into D flip-flop, clock Q, we can simply add an inverter here and name this D. So we can see when D is equal to 1, J actually equal to 1 and K actually equal to 0. We know this is going to be set, right? So Q will become 1, Q naught is going to become 0. When D is 0, then J equals to 0 and K equals to 1. So this will be reset. In this case, Q will be set to 0. Q naught will be set to 1 when clock triggers. Now, the easier version to make is T flip-flop. T actually stands for toggle. And knowing the truth table for JK, and 0, 1, 1, 0, toggle. we want to define when t is equal to 0, then q will stay the same. Q and Q0 will stay the same. However, when t is equal to 1 and the clock pulses, we want it to be toggle. That means Q next, let's say Q next is this one. Q next will be equal to Q previous inverted. Same thing for Q0. Inverted. So these two functions here, like these two rows here are the only one we care about for T flip-flop. Therefore, we can simply connect J and K together to make a T flip-flop. Sorry, I should have written this way. This is Q, this is Q0. So we see whenever t is 0, then j equals to 0, k equals to 0, and vice versa. So when t is 1, j equals to 1, k equals to 1. So that took care of all the flip-flops. Now we are going to dive into the application for sequential logic, specifically using flip-flops. And the first one is register. And for register, we usually use D flip-flop. Let's say we have a 3-bit register. Let's call this D0. Let's call this D1. D3, I mean D2. And the idea is pretty simple. So whenever the clock triggers the flip-flop, it's going to store the inputted value. So this will be our input 0, input 2, to Q, Q0, Q1, Q2. So this will be our output. Let's say, so the output will be our stored value here, as well as this one, this one. Now let's draw a timing diagram for this. So we will have D0, D1, D2. We will have output Q0, Q1, and Q2. And the clock here. And the clock pulse is going to be constant value, because not the constant value, it's going to be defined by a clock pulse generator. Like this. And assuming it is falling edge, just like the previous one. And now we usually reset the flip-flops before we turn state machine function. So our Q0 will all Q0, Q1, and Q2, our outputs will all be starting at 0 initially. For our D0 to D2, this is going to be a given value. Let's assume we give the input to D0 as a 1, 1, 0. So we know this is going to be this. And let's give the input to D0, 1, 0 next. Oh, sorry. Stays 1. This goes to 0. Let's give it 0, 0, 1 next. Okay, so when a clock pulses, the first clock pulse is this one. And basically what we want to do is that we want to check the previous value, which is going to be this column here. Now we know Q0 is going to become D0 when the clock pulse. So this will become 1. Same thing for Q1. Previous value is 1 here. And D2 is going to be staying at 0. So our Q2 is going to be Q2. Q2. Our Q2 will stay at 0. And for the next one, we will have a next clock pulse here. We want to check the previous value, which is this column here. Our D0 is 0 now, so our Q0 will go down to 0. Our Q1 will become D1, and it actually stays at 1. For our Q2, going to be staying at 0. We do the same thing again, check the clock pulse. Check the previous column, and Q0 is going to be staying at 0 because D0 is at 0. Q2 will go down to 0 because D1 was 0. Q2 will become 1 because D2, the previous state for D2 is 1. So that's how you draw the timing diagram based on the input. And notice that it basically stores the value of our input into Q0 to Q2. And this is how we define a 3-bit register. Now we can go to shift register. Shift register basically shift the value in a certain direction. And it usually uses D flip-flop as well. So let's say D, Q, clock. And we want Q, the output Q, to be connected to another input, D, of the D flip-flop. Synchronous clock here. This is going to be our input. And the Q will be, let's name this as 0, flip-flop 0, 1, 2. The output will be here. 3-bit output. Again, we assume it's falling edge. And okay, let's say our input equals to 1. Forever. The flip-flop's output assume it start at 0. So Q0, Q1, Q2. Initial state are 0, 0, 0. We have our clock pulses here. So for this cycle, we know that our previous Q0, Q1, Q2 are all 0, 0, 0, right? However, because we have an input 1, at this checkpoint here, the clock triggers the flip-flops. Therefore, our Q0 is going to become the D0 because it is connected to the input, right? So this will actually become 1, 0, 0. And for Q1 and Q2, because we know Q1, the value of Q1 is going to be depend on D1. So when the clock triggers, Q1 is equal to D1, and D1 is connected to Q0. And we know the previous value for Q1 is 0, right? So this will be 0. I mean, okay, so previous value for Q0 is connected to D1, so Q1 will become 0 because the output of Q0 is 0, previous value. And same thing for Q2. Q2 is going to be dependent on D2. We know D2 is connected to Q1, so previous value of Q1 is this one, is 0. and it's going to become 0. And then we move on to the next stage. We check this clock pulse here. Now, what's the value of Q0? Here we assume that input is going to be 1 forever. That means our input is still 1. So Q0 is going to be dependent on the input. Our input is still 1, so it stays at 1. How about Q1? Q1 is going to be dependent on D1. I mean Q1. So the previous value of Q0 actually. So the previous value of Q0 is 1. So this one will become 1. And previous value of Q1, and Q1 is connected to D2. So this will be 0. So we can see that it is actually shifting right. This will be 1, 1, 1. The next clock pulse is actually going to be 1, 1, 1 as well, because input 1, because our input is always 1. Any question? So let's cover register and shift register now. Now we can cover the bus holder. The bus holder is basically a simplified version of Latches. Basically, it connects two inverters in this way. Let's say we have an input of 1 here. We know 1 is going to pass to the inverter here, and this will become 0, right? And 0 is going to pass through the inverter at this location. And this one will become 1. Not become 1, it stays at 1. So it's like a really simple storage unit. So when we remove this input, let's say high impedance here, then this value will be staying at 0, and this value here will be staying at 1. And the reason that we are using this instead of the flip-flops is because of to reduce the area size of a silicon wafer. So let's assume we have flip-flops. Because flip-flops uses more transistors than inverters, so using this will give us a more simplified version compared to the flip-flop. Now some professor has the resistor here, so it you can modify the output, stored output, more easily, because once you set the value here, let's say let's say we set 1 here. This one becomes 0, right? And this one will become 1. And it's relatively hard to change the stored value of 1 and 0 when we input the 0 instead. So basically, this transistor here is going to compete with whatever this source is. So the inverter here is going to set this to be 1. However, this is going to compete with the inverter here and wanted to set this node to 0. And that's one of the downside of using this bus holder. I believe that's what Dr. Nourani is talking about. I can be wrong. But he mentioned that bus holder is going to be on your test, as well as all the other topics we have covered in this exam review. Okay, that sums it up for all the topics. And switch the bouncer, I don't know what this is, but Dr. Nourani said this will be on your test as well. I assume so. For traditional switch, when we push the button, because this is a physical switch, so we might have an faulty input of multiple accidental contact here. So when we are using the switch to be inputted into the clock, this is actually to give you like two folding edge and two rising edge. So instead of 1 clock pulses, we got 2 clock pulses instead. So the purpose of the switch debouncer is going to prevent the physical switch from having some accidental input. Okay. Now going back to multiplexer, because to do more problems, and let's say, okay, the problem is going to be using only Latches to realize the function f equals to, let's see, let's say A, B, C, D. Okay, now if we are not going to simplify the equation above, if we use only, because we're not allowed to use any logic gates or inverters. We have to use a 16:1 mux because of the A here, inverted A here, right? Or can we use a 8:1? 8:1 is going to give us 3 selectors. 16:1 is going to give us 4 selectors. Now let's say we chose BCD to be going into our selectors. So S2, S1, S0. We can factor that out and know that BCD selectors is going to have an input of A and B not C, D connect to the A as well. B not C, not D. Input A. And the last term is going to give us some problem because we know we selected BCD as our selectors, right? So if we dive into the circuit, gate level circuit of our mux, we can actually have inverted input for BCD. However, for our input into addresses, we don't have any inverter built into the mux. So we have to use an inverter to invert A instead. But the problem doesn't let you to do so. So if we're going to choose BCD as our S2, S1, and S0, we cannot satisfy the problem using only 8:1 mux because of the inverted A there. Therefore, we know that for 16:1, because we have 4 selectors, then for sure we will be able to put this inverted A into selector. So rewrite this function, we will get A, B, C, D. Our input line will be a 1, always. A, B, not C, D. We will have input 1. So the first term ABCD is going to be at address 15. A, B, now C, D is going to be at address, let's see, A plus 3, 11. A, B, not C, not D is going to be address 9. And A not B, C, D is going to set at address 0111, so that is 7. So So if we draw a 16 to 1, 1, 2, 16. So 0 to all the way to address 15. So we input a 1 at address 15 here with our select for select line, which is DCBA. And at address 11, we will have one input as well. So 14, 13, 12, 11 right here. 0, 0, 0. At address 8, 10, 9, 8, 0, 0. And address 7, which is this one here. So as you can see, if we select BCD, we actually require to have a 16 to 1 mux to have 4 selectors in order to have inverted variable in our terms. However, is there a way to use A to 1 to realize the function above without using any other gate and inverter? Let's say we chose ABC. We chose ABC to be our selectors instead. Rewrite the function. We will have ABC input line is D, A, B, not C, input line is D again, B, not C, not D, or B, C, D. So the D here will be going into the input of at each designated address. Like for example, ABC is address 7, right? So AB not C 101 is address 5, yeah, 5 I believe. So AB not C not will be at address 4, A not BC. This is address 3. So basically we connect D to each address, connect D at address 7, 5, 4, and 3. So we don't need any inverter for D because the Boolean equation told us that D is not inverted in any terms. So as you can see here, if we choose BCD, then we will have our A input to the address. However, we will also have A invert to some address, which choosing BCD to be our select line will not work. And the other approach to this problem is that you can even simplify F using K-map. Or Boolean algebra. then you might require to do Shannon expansion. If the variable selected to be selectors are not in each term. Like the previous example we did for this. So it's basically trial and errors here. So you look at the terms and see which selectors, which variables you want to use as selectors, and based on that, you can factor the selectors out and see if they're like any inverted input here. And also based on the problem, if your problem only allows you to use muxes and no other gates or inverter, then you will not be able to do this with selector as BCD. But however, if we choose like ABC to be our selector, then we can actually have A to 1 mux. While this has to be 16 to 1 mux. Okay, so I got an answer from, so is a latch connected to both inputs of an SR latch? Oh, so for I assume you're talking about the bus holder, so you're saying wait, oh, so okay, this doesn't work. Okay, so you're talking about switch to bouncer, right? S and R. SR latch. Yeah, that makes sense. Yeah, so due to the propagation delay of SR, the gate inside the SR latch is actually going to be able to eliminate the accidental switch here, I believe. I believe it's VDD here. Is it? So is there any more questions for the multiplexer or any of the topics we have covered in this test review. And thank you for your answer, by the way, Squid Jerky. Any more questions? Go in twice. Okay. I just checked the Discord message and I see the answer for switch debouncer. Thank you so much for your answer. If there is no question, then I think that concludes our test review for your second exam. I really thank you so much for joining the review, and I will see you for the next review. Good luck on your exams, and I hope I was able to help you with some question you have or had. Oh, sorry about this.